Hello everyone. So my name is Mihai Carabas, and today I'm going to present you bhyve-arm, current state analysis and some hardware efforts to put it on a hardware platform. A little bit about us. So I'm a PhD student at University of Bucharest. I'm also a teaching assistant there in the domains of computer architectures and networks. I've worked on FreeBSD in 2014 and 2012 on their scheduler, and also implemented some virtualization features on their vkernels. After that, I've passed to FreeBSD, working on bhyve on the instruction emulation caching, and then porting bhyve on ARM in 2015, and from then I've been working on this together with my students. A little work about porting bhyve-arm on a hardware platform was done by Nicolae Alexandru-Ivan, who is a master student also at University of Bucharest. So he helped me on finding the bugs while porting bhyve-arm. I will reiterate some of the implementation considerations for those of you who weren't at BSD Canada. So this was presented at BSD Canada in detail. So, to have a bhyve is a hypervisor that runs on CPUs that support hardware-assisted virtualization. What this means? It means that CPU vendors added a new privilege level called the hypervisor level. On Intel and AMD, it extends the current kernel mode. So basically, we are still in the kernel, and we have more instructions to deal with virtualization. On the ARM boards, they created a new privilege level called heap mode, from which the hypervisor must run. For the ARM boards, we have the monitor mode and the kernel modes when we are in secure world, and when we are in normal world, we have the heap mode, kernel mode, and user mode. When talking about Intel and AMD, these two are in the same level somehow. So, for example, in Intel and AMD, from kernel mode, you can access the heap mode instructions, and vice versa. But here, if you run code in heap mode, you cannot access the registers and instructions in kernel mode. And this comes with a problem for bhyve. Bhyve is a type 2 hypervisor, and with ARM, it's more difficult to achieve this. You have to rewrite the significant part of the base operating system, in this case FreeBSD, to use the new registers and the new instructions bring up by heap mode. Even then, you cannot run on top of that operating system's directly applications. We can compare this with Xen. Yes, you have a Xen, which is a type 1 hypervisor. It runs directly on the bare metal, and it supports running only operating systems, nothing else more. Okay? So this is a problem. We want to have a type 2 hypervisor because we want to leverage the FreeBSD management mechanism, memory management, process management, etc. And we don't want to write the full hypervisor from scratch, because we will use, for example, Xen and not bothering writing another hypervisor. To solve this problem, we insert only a small code in heap mode, basically a bridge between the host operating systems, which is FreeBSD in this case, and the underlying hardware. When the host operating system needs an operation, it basically calls the code in heap mode through some special calls and put him to execute in his name some of the operations. Other type 2 implementations are from KVM. The virtual open system guys did the same thing. Basically, they created a low-visor, they are calling, that runs in heap mode as a bridge between the host OS, their Linux, and the underlying hardware. The same mechanism. Okay, so how did we go from bhyve, from x86 AMD 64 to bhyve-arm? So as you all know, the bhyve-arm architecture is like this. You have the kernel. Inside the kernel, you have the VMM module, which is basically the hypervisor. It implements all the virtualization operations. And you have the user space part. The user space part communicates with the VMM module to a library called VMM API. And we have three user space utilities. Bhyve load, which is a user space loader. Basically, it loads the guest OS kernel into memory. Then we have bhyve, which basically runs the loaded guest. And bhyve control is more for debugging purposes and setting different settings to the virtual machine at running time. We duplicated this whole infrastructure from sysAMD64 VMM to sysARM VMM, preserving the API as much as possible. What is the reason of duplicating this? In the VMM library API, there were some registers specific to x86. And after talking with Peter Graham about this, we decided that it's very difficult to also modify the x86 interface and implement the ARM interface without causing any trouble to create a unified interface. So we basically split up the code in the interface, trying to preserve as much as I can from the x86 interface. And at a future moment in time, we will merge these interfaces. So I created a new kernel module called VMM-ARM, which manages the hypervisor state and does the context switching between the host OS and the guest operating system. Also manages the guest physical memory and other aspects like instruction emulation. We have the libvmm API ARM, so a different library for the userland to communicate with the VMM module. We have the bhyve load ARM, which is the user space bootloader, creates a virtual machine and loads the virtual machine kernel in memory. And the last but not the least, the bhyve-arm, which is the user space run loop, which emulates for now the standard input and output. We didn't create a bhyve CTL because we didn't need it at this point. So the steps I've been through to implement, I had to modify the low-level starting code, the local -v6, where I added a routine that checks if we are in heap mode, and if we are in heap mode, we install stub exception vector. So the heap mode has its own exception vector, which we'll need to populate at a later time in the VMM module. And this is why we right now install only a stub, an empty exception vector, to be able to work with it. Because we can manage this exception vector only through exceptions. It's a circle. After that, we created some low-level routines for installing the exception vector I was talking about for heap mode. The exception vector has an important entry, which is the hypervisor one. So whenever you call heap instruction, basically from the host OS, from the host OS, it raises an exception at this entry, in the hypervisor entry. This is how the modes are changed between them, between SVC and heap mode. And also implementing the code which is doing context switch between host OS and the virtual machines. This code was a little bit tedious because we basically the host OS is also a guest OS from the heap mode perspective. And we have to save all the host OS states in memory and restore it to the guest OS one, and when returning to do the same thing. And this caused a lot of host OS errors while developing, and very hard to troubleshoot. So how the host operating system, if I said you before that it's just a guest from the heap mode perspective, communicates with the heap mode and is making hypervisor call. Basically, it executes the heap instruction. The heap mode code checks from where it comes this heap instruction, not to come from a guess to corrupt our hypervisor. Then the first parameter in the heap instruction indicates the address of a routine from heap mode. So basically, the host OS is telling the heap mode code to call a function which resides in heap mode by telling it its address. To ease the implementation part, I've created a low-level interface for the Untitled hypervisor. We have a first function called vmm stub install, which it only installs an empty exception vector, the one I was talking about earlier. We have a heap init HVC, which inits the heap mode environment. It does some low-level initialization to the registers and the internal state of the hypervisor. vmm call heap is called from kernel mode to request a service from the heap mode. Using this function, we basically call different services from the heap mode. vmm set get hvbar, basically it sets the exception vector, or gets. So if you want to see what's the current exception vector, we can get it with this function, using different parameters. And the most important ones are the heap enter guest, which makes the context switch between the host and the guest and saves the host state in memory, and heap exit guest, which it makes the inverse context switch between the guest and the host. Okay, until now I've told you about processor modes and how to exchange states, but a guest needs a memory to run on it. For this, we need to map its memory. Heap mode, it's basically another address space, like the kernel. So if you have a kernel, it has its own address space. Heap mode does the same thing. Also, R, to ensure VM isolation, introduce a new mapping called a stage 2 translation. Basically, we have the original mapping between user space, between the virtual address and the physical address, and ARM introduces a new stage, stage 2, which maps the physical address of the virtual machine to the real physical address. This one in the middle is called intermediate physical address. We have an issue here because this stage 2 translation supports only LPAEE, so large physical address extension page tables, which are not available in FreeBSD 32 bits. And we cannot leverage on its memory management. Basically, we implemented the LPAE support in the VMM code. We support 40-bit physical addresses and the 3-level page table support. There are different configurations. It's very configurable, the LPAE, but we want to have a simple implementation with no bugs and didn't put accent on different mappings. This mapping would cover most platforms. Another issue is that on 42 bits we don't have direct map. What is direct map? It's an inverse mapping between the, if you know the physical address, you want to find the virtual address where it's mapped. And on 42 bits we don't have sufficient space to know this, to store and know these mappings. The solution was to create a shadow page table like the original one, but it's not retaining the physical address, it retains the virtual address of the inner page tables. Some memory mapping considerations. The hypervisor code is mapped at the same address in heap mode and in SVC mode, because when we want to call, we send the address of a function, and we want that address to be the same in heap mode and kernel mode. Also, the heap mode works with an MMU enable, using a stage 1 translation. Further, we have the memory mapping, we have the CPU state safe and context switching between them. We need a device to see if the virtual machine works. We chose the console, we have written a simple console emulation. For this, we have to implement generic MMIO emulation using traps in stage 2 translation. Basically, we didn't map the intermediate physical address, and whenever the guest the guest emulated console accesses that address, it causes an exception, and we catch that exception and we treat it by writing a character or reading a character from there, for example, for the console. So we use the BVM console that was used also in the early days of bhyve x86. Okay, we have output at this point. We need interrupts for the virtual machine to interact with devices. On ARM processor, the interrupt controller has two components, the distributor and the CPU interface. Fortunately, ARM provides a CPU virtual interface which can be used directly by the VM. So basically, it provides virtualization for the CPU interface. You only have to map the CPU virtual interface to the guest and you solve the CPU interface problem. But we have to emulate the accesses to the distributor. Basically, the distributor holds the whole configuration of the interrupt controller. So whenever the guest is doing a configuration, we have to cache this configuration and store it in memory and emulate its behavior. So basically, we register the distributed address ranges for in-kernel emulation using the MMIO infrastructure I was telling you before. We created some internal structures to retain the state of the distributor. For example, we return which RQ are enabled, which are active, their state, configurations, and so on. All the reads and writes are handled at this point. Having this information in memory, ARM processor provide us specially called list registers, LR. So it's a list of registers where we have to write the state of each interrupt in order to notify the guest about that interrupt. So the LR register contains all the active interrupts that are silent to the CPU virtual interface of the virtual machine. There is a problem here. The LR register is very small, so it has 4, 8, 16 entries depending on the platform. So if the virtual machine has multiple interrupts registered, we have to somehow handle them in the VMM code. And the last part is seeing the save state in the structures to the running state. Basically, whenever we do context switches, to get from the memory the save state in the actual distributor. Sorry. At this point, we have a virtual machine that ends up with some supervised interrupts because of a bug in the emulation path. I guess we are not restoring very well the LR registers. So basically, we are marking some active interrupts when they are not, and the guest receives that interrupts and doesn't know what is with it. It's very hard to debug because it's all in assembler code, and we didn't find the point where the bug is at this point. For now, we are using two unused timers to not virtualize a timer, SP804, and we've mapped this directly to the host. We want to expose the generic timer using the virtual timer feature of the ARM processors. About the development platform, at first we used FastModels because we have the model debugger and we were able to connect to the fast model and see what is executing, see what's the state of the registers in different modes. It needs a license for ARM. If you want to try it, it's a 60 days evaluation, I guess. Further, we wanted to run bhyve-arm or real hardware platform. We had two boards in our hands. We started with the Samsung Exynos, but unfortunately the board burnt out, I guess 6 months ago when we were playing with it. And then we jumped out on QB2. the behavior of the problems running bhyve-arm with these two was the same. The code, first of all, the code we were using for the emulator was very old, from April 2015, and meanwhile, the boards were putting up, and meanwhile, there was modification last year on the head. So we did a rebase with the current head, fixed the local, some local conflicts, and then fix the problems with the virtual interrupt controller introduced by IntiNG, because here we had also some conflicts, and get the latest U-boot which left the boards in hit mode. Unfortunately, the HVC instructions was causing an undefined instruction exception. This means that the boards were somehow not supporting virtualization. And we didn't understand why, because with the same U-boot, we were able to boot Linux and run QEMU with KVM with no problem. And so the same binary, not recompiled. We found out that there are two paths in U-boot in order to boot a kernel. The bootm path, which Linux uses and which enables the virtualization, and the go path, the go command, which FreeBSD kernel is using and didn't have the bits of the virtualization needs. So basically, the U-boot, when starting with go, it didn't activate hit mode. Actually, it activated hit mode, but was leaving the board in an SVC mode, not hit mode, as we needed. We patched the go flow for RAM in order to enter the kernel in hit mode. Also, after this, we find some bugs in the low-level code. The altr simple instruction was used to load various labels, but this requires that the labels to be in the 4K range, and there weren't, and the instruction caused some invalid addresses, and the boards were failing when trying to load that address. We moved the label. We have one label, important label, closer using a temporary symbol table, and also we have to change from RDR to ADR because the RDR is loading the label address, not the address in the table. The current status. We are running a bhyve. We are running a virtual machine, a FreeBSD virtual machine with bhyve on ARM. We have the output to a para-virtualized serial console. It's getting to the init process, but it gets flooded with spurious interrupts. Here is a snippet. So you see that it's printing, copyrights, and all the init stuff. The memory it has available, 128 megabytes, and so on. It initialized the interrupt controller. You see here that are multiple writes and reads to the distributor. We have the timers, the SP804 event timer, which is initialized, and after that we are getting spurious interrupts. Again, probably for the wrong-based register configuration. The next steps would be to add SMP support. Basically, we have to execute the initialization code for hit mode on all processors, and also add some logs. Emulate more devices, at least a serial console on a disk, to be able to run, for example, a Linux guest. And the most important project would be the porting bhyve-arm on ARM v8, because we are now supporting FreeBSD on ARM v8, and more servers are coming, and virtualization is a must on there. But first, I want to solve that bug regarding the interrupt controller. Okay, thank you very much for your attention. If you have any questions, I will be pleased to answer them. Yes?
What do you know about the So what do you know about the spurious interrupts issue? I've seen that on bare metal hardware, like the Samsung Chromebooks.
Yes, but on some boards appears at some level some spurious interrupts, but here the VM is flooded, so these are continuously appearing. Probably we watched on the interrupt control implementation of the guest, and we saw that the spurious interrupt condition is when an interrupt is received, but the interrupt controller didn't know about it, so didn't register any interrupt. What we are guessing is an inconsistent list register content in the hypervisor. We are not restoring this, okay. So it's a little bit different than the boards that are giving some spurious interrupt at some point. Okay. So here it's a generic problem. I hope in the next month to solve this. Okay. Okay. Thank you.